Thanks, Tony, for the introduction. Happy to be here today to share you details on this project we call the GRAPS project around here at MGS. So I'll tell you all about GRAPS, what it means, and what we did here today. This is a pilot project, so a lot of this was really a chance for all of the names you see on the screen there who were involved in this project or one way or another. It was really an exercise in thought. It was we felt like we were sort of the R&D team at MGS for the last year and a half or so. We really had a great chance to sort of go over all of our mapping methods, thinking about how to compile maps into the future, thinking about the future of CGAs and how we visualize them and show them and communicate them to planners and the public and so on. So I'm only the PI or the one talking here today. All of this work was put together through everybody on the screen here: Andrew Retzler, Jackie Hamilton, Jen McDonald, Caleb Wagner, and Bob Tipping and Carrie Raber at MDH. And Gus Carlson, some of his work I'll show you. He is an undergrad at the U of M department. So I'll tell you about the GRAPS program. I'll tell you about our pilot project with MDH and GRAPS. We'll go over the project watersheds that we started with and the products. I'll tell you probably more detailed information than you'd ever want to know about mapping and compilation methods for the Quaternary and the Bedrock at MGS. And I'll show you what we came up with, the compiled watershed models and maps, and this product we're calling the texture dot model for the Quaternary. And then there'll be some time for discussion too at the end. This talk is really for all of you to, for these purposes, but it's a little bit selfish too for me too. I'm curious what you all think about how we've decided to showcase this work and thinking about ways it can be used into the future. So hopefully there'll be some time for discussion at the end. So the GRAPS program, what is GRAPS? What does it stand for? Groundwater Restoration and Protection Strategies. It's an MDH coordinated program designed to support watershed planning efforts. It helps local planning efforts prioritize groundwater quality and quantity concerns and provides strategies and action for protection and restoration. And they do that through very comprehensive GRAPS reports, what they're calling them. And GRAPS, there's 18 GRAPS reports for individual watersheds so far that are completed. If I have my numbers right, last time I checked. And they're basically a collection of maps and data describing the watershed conditions. And they're, it's only coordinated by MDH. It's definitely a multi-state agency contribution. Bowser, MDA, and DNR, MPCA work all come together to help put together data and create those reports. Notice I didn't say MGS. General geologic information absolutely exists in these reports, but it's not often containing the most detailed information available from the MGS, mostly from our County Geologic Atlas mapping program. So here's just a cover of what the Zumbro GRAPS report looks like, and here's a snippet of a geologic map from the Zumbro. And if you're familiar with our products and CGAs, you know that we can definitely fill in some better groundwater information than what's depicted there. So this was really, that was this project goal for MDH MGS. Our pilot project, 2-year pilot project, was to try to provide a compilation of surface and subsurface geologic data within a selected watershed for modelers, but also planners and the general public to get something out of, to use. And we wanted that to be 3D. We wanted it to include both bedrock and unconsolidated deposits, and we wanted it to clearly depict aquifers and confining units. And we wanted it to be viewed in a browser, so no GIS software would be needed. And we wanted this to be a tool basically for understanding differences in water quality between and within aquifers, to address that need of making the invisible visible, making groundwater visible, right? So how would you do that? We started with our CGA information, and we thought long and hard about how we can repackage that into a meaningful way to allow the users to explore and layer 3D data to make more informed decisions. And we recognize that, well, CGAs are widely used and recognized in the state. However, we recognize at MGS that when planning at larger scales that involve several counties, for instance, a watershed, like most planning is done through the state these days, it's can often be problematic for users to create seamless geologic and hydrogeologic data sets when you're dealing with sometimes a watershed of 4, 5, or 6 counties in one. And we also wanted to generalize this. You know, our maps can be highly technical and complex and a bit hard to digest at times. And we just wanted to make something that had all the technical information, but could also be generalized down by texture into sort of the obvious hydrogeologic properties of coarse, fine, and mix. So you'll see some examples of how we did that. And like I said before, right at the get-go, this was really our chance to review MGS mapping and MGS GIS processes, and to think beyond the cross-section approach, especially in the quaternary methods. So here's the watersheds we started off with. We've got St. Louis watershed in northeast Minnesota, and we did the Zumbro River watershed in southeast Minnesota. So we've got those completed. Those are the ones I'm going to show you some images from today. And this coming year, this year and beyond, we're working to compile both the Missouri, the Cannon, and the Red Eye. The Zumbro River watershed in southeast Minnesota spans 6 counties: Wabasha, Rice, Goodhue, Olmsted, Dodge, and Steele. And those numbers in parentheses are their MGS CGA publication dates. So you can see that there is a wide variation in dates going back from 1995 to maps that are mostly completed and just not out the door yet, in progress. So our products over the years have definitely changed. Some of those older counties have no quaternary cross-section subsurface information. And the degree to which the mapping data sets align when you pull up 2 counties right next to each other is variable as well. And we chose Zumbro because that's with MDH's help that they wanted to focus on Zumbro, and they were also interested in St. Louis to start with. Some of our work was already followed up by groundwater modeling of travel time by Bar Engineering near drinking water supply management areas. And it was just work to support delineation of wellhead protection agencies. So some of this work is already, it's fresh and it's already being modeled. And the St. Louis watershed, that one spans 5 northeast Minnesota counties: Aiken, St. Louis, and Lake, are all currently being worked on, and county geologic atlases are being mapped in progress right now. Carleton County was the only one that had an existing CGA from 2009. And Itasca had no information from a county geologic atlas yet. So some new subsurface quaternary mapping was done through cross sections to fill in that area. One thing to note, the St. Louis watershed information that we put together is only quaternary and does not include bedrock surfaces beneath the bedrock. The Zumbro one does, because those are the Paleozoic layers. And but we do include bedrock topography for St. Louis, so it's a quaternary model mostly. And we chose St. Louis because of MDH's interest, and also because it's a sensitive area where fractured bedrock is near the surface and distribution of those quaternary units and their textures is important to understanding things like recharge and pollution sensitivity in that area. So superficial geologic maps, superficial quaternary geologic maps are depicting the unconsolidated sediments encountered within just the first few meters of the land surface, and we refer to that as superficial geology. Map units, quaternary map units, are distinguished from one another by texture, lithology of this very coarse grained sand fraction, the 1 to 2 millimeter sand fraction, and their stratigraphic and landscape position and geomorphic expression. We were able to use what Barb Lusardi and others have put together for the statewide superficial map. And basically that is a statewide quaternary map shown here, where the whole state of Minnesota has been linked together and compiled for the superficial geology. And all we really had to do for GRAPS is to add in and compile any new maps since S23 was completed, which is very new. The actual year is only, I can't remember the actual year, but it's probably 2018 or something like that. So the only new Atlas products were Dodge and Olmsted that had to be linked in and edge matched in the Zumbro for the superficial geology. And here, Jen McDonald did the superficial geologic work in the Zumbro. So here you can see her superficial map. She had 18 superficial geologic units in the Zumbro River watershed. You know, they range from anything from alluvium, colluvium, terrace, glacial lacustrine to several of the different glacial till formations. And she had a unit for bedrock as well and residuum. Subsurface quaternary mapping at MGS is accomplished by creating a series of cross sections. And so we followed that same approach for the GRAPS project. We tried to simplify it and reduce time required to make a subsurface geologic model. And we chose to do cross-section work every 5 kilometers instead of our standard 1 kilometer spacing. So a geologist, you know, has the watershed, has their cross-section lines going across it, and looks at the well data along each cross-section and is able to delineate units and tills and so on. So that was done for 12 east-west cross-sections every 5 kilometers in the Zumbro. And they were taking advantage of existing ones, newer ones from the Dodge and Olmsted atlases, and new ones had to be made in counties where subsurface cross-sections didn't exist, where those atlases were not as recent. And so it just involves a series of putting 2 cross-sections together and doing some edge matching and getting all the units to work out. And from these cross-sections, if you're not familiar, I learned a lot about this whole process going through here with Jen, but basically, and Jackie, our GIS expert on the project. Basically, in order to create the map view, or the subsurface blobs, for lack of a better word coming out of my mouth right now, is you take what you've got in cross-section, and coordinates and elevations from the quaternary units in cross-sections are extracted along the cross-section lines and used to create a model in the for distribution in the subsurface. So I don't know off the top of my head, but I believe this one might be the Allendale till distribution if you're looking at it in map view, and that's a modeled distribution based on the different cross sections drawn by the geologist. So that's a bit about the process there. There were 11 subsurface quaternary units in the Zumbro, for which Jen had mapped in cross-section and modeled as well. And for each one of those units, she had provided a USDA generalized soil texture for each one. Each one was either determined to be a loam or a clay loam based on all the texture information that she's was used to compile those units. And here's just an example of all the different units that she mapped and their USDA texture for each one. We simplified that even further into what we call a generalized model texture for the online browser model that was either sand and gravel, clay, or mixed. So for the Zumbro, it's just 3 generalized textures in the model. I'll show you in a minute here. Bedrock compilation methods. Bedrock topography is just the elevation of the bedrock surface, and individual lithologic units, surfaces are made for each of those units. That's standard what we do for our CGA maps. And here's an example of what those look like stacked up for Olmsted County from the Olmsted County Geologic Atlas. And those are just made by, taking contours of a specific top. A lot of times we use, say, the Jordan sandstone top, contouring the elevation of the top of a specific unit, and then adding up or adding down based on the thicknesses of units above and below. So it's a much different method of making a geologic map than the Quaternary process. So individual surfaces are contoured. And in terms of Zumbro, mostly we were able to just pull from existing County Geologic Atlas information. Andrew did do some new mapping in the area of Wabasha, where a lot of those Paleozoic faults are located. So some of that was cleaned up in the surfaces for modeling. So this is what Andrew was able to pull together for our geologic model. We were really impressed with how it turned out. This link will take you right there if you want to copy that down and play around with it. It's totally interactive. You can click on it, move it around, turn it upside down, that sort of thing. He's got all units turned on right now, but you can turn one off and turn one on. Right now I'm just showing bedrock geology, but the whole system is there. You can turn on the subsurface glacial geology and the superficial map as well. So it's all 3-dimensional. He's got units all the way from the Spillville in the Devonian part of the section all the way down to the Mount Simon at depth. Okay. For the Quaternary, we decided to use dots, or what we call a texture-based point model, to visualize textures in the Quaternary below the ground surface all the way to bedrock. And it was a really neat way to visualize the whole system with the Quaternary and the bedrock all in one, a whole subsurface complete system, because you're able to sort of look through the dots and kind of see the Paleozoic units below. And I'll show you an example where they're all together. The Quaternary subsurface dots in the model are spaced. Thing here, and there's nearly 1.3 million points in the model. They're spaced every 250 meters by 250 meters in the XY direction, and there's a dot for texture every 5 feet. And they're based on, you're seeing 3 colors here. Clay is, or the tills are brown. A mixed clay and sand values are this magenta purple color, and sand is noted as that tannish orangish yellow. And what you're looking at here is even a smaller subset of the model spacing. I believe Andrew used 500 by 500 meters by 20 feet in the vertical, was chosen to just for ease of on your eyes. You're seeing less points overall. So that's the spacing of the matrix in the browser model. And 3 modeling processes were used to populate what texture goes where. And that's a superficial map process, a subsurface map process, and an interpolated map model process, which I'll go over how we got all those next. So here's the superficial map, the generalized superficial map. So it's just taking Jen's superficial, compiled superficial map for the whole watershed and then just generalizing it into 3 categories, the same 3 categories, the same colors you're going to keep seeing here, the sand and gravel and the mixed, or the sand and gravel, the mixed, and the clay. So you can see Zumbro, if you're not familiar with the geology of the area, it's definitely has more till in the western, and it's thicker in the west, and then the sand is focused in the bedrock valleys. So for the superficial, to fill in the dots in the matrix, to fill in the texture and find the dots in the matrix, I'm going to go through this in my little model here. You basically just intersect the superficial map to that uppermost point. So the uppermost point in the whole matrix is just an intersection with this generalized superficial map. So it's just taken right from here. The subsurface texture points are a little bit more complicated, but basically we're just using those rasters that Jen put together. And the point matrix was just intersected with those 11 quaternary rasters and assign that unit's texture if their elevation was within the elevation range of that, that unit. So here's a model of how that gets done. Here's a modeled line of the top of a particular unit and the bottom of that particular unit, and that would have had a texture with a mixed value. Okay. The last way a dot or texture gets determined or modeled is through something called an interpolated texture. And that's a process built by Bob Tipping when he was with MGS, where it's just applying ordinary creating estimation and prediction standard error methods on the current lithology data listed in CWI. So here's a well record from CWI with the geologic material described by the driller, and there's a table in CWI with the actual lithology. So this one's pretty straightforward. The driller describes gray clay, then that stratigraphy table is just called gray clay. And it's just an estimate of the likelihood of sand, mixed, or clay values in the subsurface based on averaging out all those all of that lithology data. So here's what that looks like. Here's where you can tell there's a lot of clay and till off in the western portion of the watershed in the subsurface, and the sands are also depicted in the valleys as similar to what Jen has mapped. So it's totally interpolated from CWI. So here's what it looks like all together. Again, you can zoom in, zoom out, play around with this model if you go right to this site. But I thought it turned out really nice, how you can see the quaternary subsurface information. You can see where the texture is coarse versus fine, and you can see where it even starts to thin or become, very dissected in areas where there aren't any dots as well. So putting all of those 3 interpolated models did create some overlapping points, and what we decided to do in terms of that hierarchy of where do you pull texture information, what's the best source for each of these points, for our recommendations, it's using the superficial map first for that uppermost dot, and then it's taking those interpolated sand values and using that to determine where the sand is in the subsurface. And then it's using the subsurface model from the quaternary rasters that Jen put together. And it's a giant set of dots, 1.3 million points. Each of those points has a specific location code or attribute with their specific UTM coordinates and its elevation. So a lot of this stuff can be individually queried and worked with in ArcGIS as well. So again, here's just what it would look like all together if you pulled it up and saw the model. It's got some base map information, and if I didn't say it already, the individual surfaces can be turned on or off depending on what you're looking at. You can turn off the dots or turn on the dots, or turn off individual bedrock layers. You can search, say you have a particular town or an address, you can go right there and search right to it, and so on. And this work you're seeing here is what Gus Carlson was able to put together with nitrate data from wells, private and public wells. And Gus was able to put together several rasters of the probability of elevated nitrate. And he did this for a few different units. This one you're looking at is the probability of elevated nitrate in the upper carbonate aquifers above the Decorah Shale. And you can see when you, it's just one way of, one method of using this information or seeing these maps is you can see that the elevated nitrate in the upper carbonate aquifers is tied very much to its geologic setting. It happens where the tills start to fall apart and become dissected and thin along this edge. And that's where you're seeing the elevated nitrate. He did this for the Jordan as well. Elevated nitrate in the Jordan values are those darker green colors jumping out at you, and that is areas where the Jordan is dissected and is first bedrock, and all in areas where the Decorah Shale is non-existent. This is the distribution of Decorah Shale. So just some different ways to use the geologic data sets and use them for comparison purposes and looking at geochemical values. All right, well, this St. Louis set is pretty similar in terms of methods, so I won't go through the whole spiel again, but I'll get started with that. As I said before, St. Louis, we compiled the bedrock topography from our in progress CGA mapping, but we didn't do any bedrock geologic surfaces at depth. And well, I guess you can just see, I'll describe the bedrock topography. It's very unique. It has high relief from 1,500 feet above sea level up in the red areas down to very low values below hundreds of feet below sea level down by Lake Superior. So it's a unique bedrock topography setting. Caleb Wagner did the Quaternary work mostly with Jen in the St. Louis River watershed for the superficial maps. You can see here's his total or all superficial geologic units shown on the map here in the watershed. I can't remember off the top of my head. I think I have it on the next slide, but several more units. It's a bit more complex up there in terms of glacial stratigraphy. So he's got many units in the glacial superficial map there. And what we chose, we did St. Louis after Zembro, and we chose to not only include clay, mixed values, and sand, but to also generalize two other textures, a peat and a lake combined texture, as well as a bedrock texture, where anywhere there's this outcrop, basically rock right at the surface. So those 5 textures are in there. Here's what the model looks like overall. So you can see the bedrock topography dropping down here, and the points on top of that. Again, same color scheme. The tills are going to be brown, and the clay is going to, and the till and clay is going to be brown. The sand is going to be tan and yellow, and then the mixed values are that purple color coming through. Again, the methods to build the texture model and populate it are all the same as the Zembro that I went through in detail. The St. Louis River watershed is a bit larger, so it includes 1.7 million points. And it includes both the superficial, the subsurface, and the interpolated methods for finding those texture values and populating those dots. Again, because of its size, 27 east-west cross sections were done every 5 kilometers. And we did take advantage, we didn't draw new cross sections if existing county geologic atlases were there. We took advantage of the existing work that's already been done and in progress for St. Louis Lake and Carlton. But we did do some new mapping in Aiken and Itasca where we didn't have products available. Here's where I have that down. Overall, within the St. Louis watershed, a total of 68 units were differentiated in the Quaternary, 40 in the superficial and 34 in the subsurface. And some of those are the same unit and have a unit in both cases. In northern Minnesota, one thing Caleb found was many of the subsurface glacial till units mapped by the geologists are rocky, but described as a driller as sandy. So we did have to take special consideration in and really looking at that interpolated sand dot model that we do and comparing it back and forth to a lot of the cross-section work that Caleb and Jen did to try to really make sure that interpolated sand model was capturing the right amount of sand. So we took it back a few percentages in terms of probability. A lot of those details probably don't matter to you if you don't work with this stuff, but a little bit less probability we use to account for the sand, just because of the setting up there. So we can get into the modeling artifacts discussion a bit here. So here's some examples of those, you know, how we make the model, how we produce a unit in the subsurface based on the cross-section work. And here's what our Zumbro model looks like if you just stacked all the units on top of each other. So, you know, it is, you know, using 5 kilometer cross sections really did simplify and generalize things a lot more than we would have liked. And another modeling artifact is that the model matches the cross sections well. When you get off cross section space, it's where things sort of fall apart. So, and as you can also see, there's a lot of linearity that goes on in this method, both in terms of elevation and map unit extent. There are some unintended gaps where one unit, you know, it just doesn't go as far in one direction as you might have liked if you were actually drawing these things out. It's a model, right? There's oversimplification done, and that's what I, you know, when I stare at this stuff, I go, why can't we make more geologic sense? And then I'm told, well, it's just a model. It's just a model. So, but maybe this is just my plea here for the Quaternary folks. It really is something we are looking to improve. And for instance, you know, as we were looking through a lot of this and populating textures with dots, we noticed, oh, there's a lot of dots that are not populated. There's a lot of gaps in this towards the bottom. And so we found that the base of our units needs to be taken all the way down to bedrock topography. They weren't matching up like we thought they should have been. So that's one outcome of this GRAPS work that sort of changed how we do things in CGA world. So that was a really nice find and catch that we're now fixing in products going forward. I do want to say too that, you know, this was a project focused on review of quaternary mapping processes. So we inevitably found these problems. And we inevitably found ways in which we could improve our CGAs. But I do want to say, you know, the incredible work that the quaternary mappers do. I mean, the amount of effort that goes into these quaternary maps and the counting of the grains that gets done, it's incredible. I've always been blown away by how, you know, how detailed they are. And it really was only recently, right, 2016, where we've sort of got the Bible or the formalized lithostratigraphic nomenclature set for, you know, these ever so complex quaternary units in Minnesota. And, you know, and it's the devotion of our GIS staff too over the years that have really, you know, been able to develop this model and show that we have all these quaternary units in the subsurface. And it really is quite detailed and exemplary from what other states are doing. But I always think there's room to build upon these and improve. And I am sort of hoping to make them more geologic in the subsurface. I think that we can work together and get some more Quaternary staff closely involved in this modeling process to try to fix that, try to improve upon that. So here's where I was going to put a joke. So I don't know if Bob made it in time to this or not, but
yeah, Bob is with us.
Hi, Bob. Bob has a tendency of losing his shoes on the outcrop, or sometimes only coming to a field day with only one shoe. But Bob, I found your shoes, and I think you left them at MGS, and I have both pairs, or I have both, but my feet are really small, so they don't fit me. That's my joke for the day. Sorry, I'm not really all that funny, but you know, this is Bob. This is work that Bob's been doing over the years. You know, he's always been our champion to sort of reduce the errors and redundancy and you know, help us with finalizing better subsurface models. He's always, you know, championed quantifying the uncertainty in the modeling in the subsurface, in the sands. And it's really, this is all built upon his ideas and his work from what he's written up in the Bonanza Valley groundwater open file report. So if this stuff really interests you, just please know that that open file with all this, with a lot more detail for some of these processes is in there, and to check that out. And in there, you know, he's describing a lot of this stuff, you know, that we need to quantify uncertainty. We need to find better methods in the subsurface to remain current with shorter time frames. So as you know, as the idea is that as new logs and wells become available, you know, our till stratigraphy that we've gotten worked out will remain relatively static. And this is just a way we're using dots to try to better correlate sand bodies over time, to redo it, you know, from time to time as needed when new data become available. So this is a step towards that. And I do just want to shout out that we do realize that this does impact Part B geologic sensitivity mapping methods, and that is discussions we want to continue going forward with Part B mappers and Todd and others at DNR. So in terms of future work, we do recognize that, you know, we have a browser, we have this model, and we have these open file reports that talk about what we did. There's no information yet really for supporting text from a hydrogeologic perspective. So that's something we hope to do in the future with MDH and the GRAPS program, is to sort of figure out how this is going to be presented to the public, and how to best have supporting text in some format on the browser, you know, linkable or right next to it somehow. And like I said, it's been very well received from several different places we've presented this to, including the Interagency Groundwater and Drinking Water team, with a quote from one person there is, "How can we get more of these and how fast can we get them?" And our response to that is, thank you. We think these are great too, but we don't want to get too far ahead of ourselves. Going forward, we see this as a tool to support CGAs and not compete with it, right? We want to keep new mapping done through the CGA program. There's so much base work and background work and locating and things that get done through a wholly funded CGA program that doesn't happen in this GRAPS work. And so we want to keep that process going, because that's really the best way to keep making good geologic maps. And but we do want to listen to health, and we are willing to, we want to keep going with this watershed scale mapping. So we'll focus on compiling and generalizing existing CGA data sets in watersheds that most need this information for modeling and so on. And we will agree to doing limited mapping in smaller portions that may need it along certain county boundaries if they don't have one yet. And for instance, in this coming year, we're doing some of those other watersheds like the Missouri and the Red Eye, and not all of them have CGA products yet. So we're kind of thinking of a way to visualize how we showcase one county that has really great subsurface data versus another county that doesn't. So we're working through some of those issues right now. And pie in the sky, someday maybe we'll be able to map Quaternary sediments in plain view rather than going from the cross sections into the model. But that's I think we're still in agreement that that's a little bit far off, but something we're definitely hoping to play with in the future. So I think I'll stop there. Here's our open file reports if you want to find more information on those 2 watersheds. And there's also an MGWA news link there. We had a short description of the project in there as well. So thanks for listening.